Great, so let's get into this. I will start by sharing my desktop with you. And you're now looking at our, my Excel spreadsheet, and you can see I have loaded at-risk 6. Now, some of you might be interested in following along with the examples that I'll be going through in today's webinar. I'll only be using the example spreadsheets that come with the software, so if you do have, at-risk professional or industrial, which is the necessary addition for the project interface, then you'll be able to use the example spreadsheets as well. For those of you who either don't have at-risk for Excel currently, don't have version 6, or only have at-risk 6 standard, you don't have access to this interface, but you can always download a trial version from our website, and then you'll be able to utilize the same example files that we're going to look through. So first I'll start with a few introductory words about stochastic modeling or risk analysis or quantitative decision modeling to begin with. Now, usually in a project environment, we are often asked the following questions. How much will the project cost? And when will we be done? Okay. Now, standard modeling practices attempt to answer these questions using deterministic models. The cost will come out at an exact figure, maybe 120 million, and perhaps the duration will be in a number of days, or more likely in a date such as the 15th of June 2014. That will be our finishing date. Of course, the problem with this is that to arrive at either of these numbers, everything has to actually happen exactly as we have that figure in our spreadsheet model currently. Every cost needs to be exactly what we estimate it to be. Every task must be completed as we expect it to, and so forth. A more important question, a more realistic one, is what is the probability that we will get a project done under a particular budget or for a certain amount of money? And also, what is the chance that we will finish by a certain date? These are the questions that are both very useful and only answerable via probabilistic or stochastic modeling, the sort of modeling that is done by at-risk. Beyond those basic questions, we can also ask questions about what are the key risks, be they costs, tasks, or in both cases, key risk events, threats or opportunities that will influence or impact our ability to get the job done for a certain amount of money or in a certain time. What we'd of course like to do is to generate a distribution of potential costs and finish dates or durations, and utilize that mostly to describe statistically what might occur. Now, pardon me, traditionally these two aspects of project management have been separated. This is the cost component and the schedule risk component. We can keep them separate if we choose to. However, utilizing at-risk 6, we can also combine these in a single spreadsheet model. So what I'm going to show you today is how at-risk allows you to interface with MS Project in a spreadsheet. And as you know, if you've got something in a spreadsheet, then you can simply add more cells, formulas, functions, tabs, etc. To that spreadsheet to represent other components. So we will look at not just modeling a schedule in Excel, but also including external risk events and so on in the schedule. And you'll also see that by putting the schedule into an Excel spreadsheet, you will have particular cells representing dates or durations, start dates, and so on, and these can be logically linked to any other part of your model, including the cost model. Okay, so we will focus, of course, primarily on schedules, but also look at costs within those schedules, pardon me, as well as showing you the main features of the project interface. You can get rid of all of that. So let's start by looking at our example files. For those who don't know, the example files are in the Help Example Spreadsheets section of the at-risk ribbon. You'll then see that in Product Features, there is a section called Simulation with Microsoft Project. I click that hyperlink, and it sends me down here to the examples that come with the software. Okay, just a quick word on our example spreadsheets. All of these, pardon me, sometimes referenced in multiple places on the spreadsheet, pardon me, such as here. Some of the models come with videos. This is a selection of short video tutorials showing you how to utilize that particular model. So you can watch the video and then do the analysis or simulation yourself. Some of the example files are also both part of a particular business field and a product feature. So they might be in several places, and that diamond icon in the bottom left-hand corner, that indicates that those models themselves are related, or that model exists also somewhere else. So you can navigate around this page using all of those aspects. Pardon me. Likewise, there are just other general videos available to you on the website, and I suggest you do go and look at those. There will be some that are general to the software, some that are specific to certain features, but there's lots of good information there, and they're all quite short, so it's easy to see. Not necessarily you have to sit down for hours to watch the video. So let's have a look at an example, pardon me, and I will start with the tutorial example. Now, what happens when I open this spreadsheet, you can see very briefly there, MS Project itself opened. So this workbook called tutorial.xlsx is linked directly to this schedule. So the way, or the general usage of the product will be to either create in MS Project a schedule or build it in some other system and then export it to MS Project so that you can use the features of the interface. It may be that you have a very large schedule that you've created in a different piece of software. Maybe it's got tens of thousands of line items, but that's beyond the scope of any meaningful analysis when it comes to simulation modeling. So you may have those rolled up into subtasks or subcategories, and then that can be placed into MS Project, and then we can link it to a spreadsheet model. I'll show you how to do that linking shortly, but here's one that's already been created. Pardon me. All of our example spreadsheets, just so you know, has an explanation page, which is very useful, letting you know what's going on, as well as some potential expanded ideas or progressions you could make from the model that is in here already. Now, this tasks section and the resources section are full of information that was taken directly from the project itself, this .mpp file. And it's placed it into Excel. What it hasn't done is placed just a photograph of the schedule into the model. This is actually a working live Gantt chart, if you like. And the two files are permanently synced. If you update one, you can set it to then update the other, and so on. The idea is that they're now a working pair that need to represent the same information. If someone updates the project file, the next time you open the spreadsheet, those changes should then be reflected. Let's have a look at this little example and see what's actually been done. My project has been placed almost exactly into a spreadsheet, but this is just a regular spreadsheet. All of these cells simply have numbers in them. Although at-risk is smart enough to know that this is a schedule, and therefore we'll see later we can reference these text columns, so these text cells, and it actually knows that that is a particular task. An example of the inclusion of at-risk in that model then is instead of a 3-day duration for the upgrade hardware phase, I actually have a distribution for that duration. It is just a number in a cell in a spreadsheet, therefore I can use at-risk. So those of you who are already familiar with at-risk, or what we previously referred to as at-risk for Excel, using at-risk 6 with scheduling is in many ways identical. We're simply going to get or put probability distributions into the appropriate parts of the spreadsheet and then run a simulation. I have both durations and in this case also a start date that is variable. And those are the two key features of the Gantt chart that will vary: start dates and durations. Finish dates vary because of those two things. And while you can apply a probability distribution to a finish date, you really should be looking at varying either the duration or the start date, and then allowing the software to calculate then the new finish date. But the true variables are the start date and the duration. Now, there's no limitation to the sorts of variation I can put into my model. This is at risk for Excel, or we used to call at risk for Excel just at risk 6. So I have the full, pardon me, the full range of distributions that I can put into my model. I could use discrete distributions to have in full day durations. I can use continuous distributions to have fractional durations, and so on. Or indeed combine different functionality or multiple functions into a single cell. At risk simply wants to read off a number in there that works as a duration. Likewise, something that works as a date. And you can see in this syntax, there is a risk is date function. That's a function many of you may not be aware of. Something that allows at risk to explicitly acknowledge that a particular input or an output is a date, and therefore in terms of reporting, graphing and so on, statistics, it treats it as a date and allows you to use date values in there. Now, in this particular model, it's a simple little model. We only have a few probability distributions included, one for the start date of defined training objectives, the duration of upgrade the hardware, and the duration of acquire training materials. I'm going to include another one here for conduct user training. So I will use my right-click shortcut to define a distribution for conduct user training. It's currently 5 days, and instead I'm going to use a log norm alt function to represent the uncertainty. So this interface is of course exactly the same as you would have using Excel. It just happens to be now being applied to a schedule. Now, within the fields itself, you notice a static value has a special value here called project field val. This is, pardon me, the value that was placed initially in our project schedule itself in MS Project. And this is a keyword that actually takes that number and then uses it. Therefore, the Gantt chart and the values shown in the spreadsheet directly here are the equivalent of your base pardon me, schedule that you built. Now I'm going to include some extra information here. I'll say my P50 is 5, maybe as low as 4, and as high as 10. So I've now used, make it a bit smaller, 8. So I now have a log normal alternate parameter distribution that I've constructed using percentiles, pardon me, instead of mean and standard deviation, to create a distribution for the user training phase, where generally it will happen as I expected, around 5 days, but there's a chance that it could take twice as long or even longer, I guess depending on how long it takes to upskill my staff. So I click OK, and this is the log norm alt function that has been included in the spreadsheet. Pardon me. I also have an output here, which is my finish date for the training phase. And I'll run a quick simulation for you, and let's see what that finish date looks like. That was a quick simulation of 100 iterations, just as we would do for a regular spreadsheet model. However, it happens to, in this case, be looking at the relationships that we've built in our schedule and modeling those correctly, doing those calculations to come up with a finish date. You'll notice there are gaps here because the project can't finish on a weekend. Pardon me. And so we have a range of potential finish dates. From here it's from the 5th of November to the 3rd of December. Okay, so during a simulation itself, the random sampling that occurs for these durations and start date are actually being placed into the schedule itself. Therefore, all of the rules of the schedule are still being employed. So rules about finish to start and so on, these are all maintained during the simulation. Therefore, the simulation results will be as realistic as the schedule that you've created in the first place. So I'll now go and add an output to the duration itself. So I simply go to my duration cell, click Add Output. I'll run a simulation here, a little bit bigger, 500 iterations. And here is the distribution for my total duration. I still have here a distribution for my finish date. And all of the results that I'm used to being able to see in at-risk are of course available to me for these project-specific outcomes, including but certainly not limited to sensitivity information. So I'll look at which of my inputs is affecting, in this case, the average finish date, or I can change that to look at the downside. So let's have a look at which of my variables have the greatest impact on the P90 of my finish date. And I see that the conduct user training, although it doesn't have such a broad spread of impact, it's the one that can cause the finish date, or the P90 of the finish date, to be the longest. Okay, so all of our standard results and the sorts of interpretations we would want to get out of our various tornado charts, for example, or out of our graph to begin with, these are all still maintained. You just happen to be talking about a schedule now. Pardon me. So we've seen the basic idea. We have a schedule. We link it to an Excel spreadsheet, and I'll show an example of that right now. We then identify our uncertainties, place at-risk functions in those cells, run a simulation, and get the relevant results. So apart from the initial piece where we need to import a .mpp file, the rest of it works exactly the same as regular, if you like, Excel modeling with at-risk works. There are a few components to schedule modeling that are specific to scheduling, and therefore we have some extra tools in here. And they're the things that I will show you. But I did want to make it quite clear that once you've got your schedule in Excel, all of your current Excel skills, or at-risk in Excel skills, are completely applicable. So let's start from the start, and what I will do is import a file. So consider that we've already built a .mpp file somewhere, and now I'm going to import one. So I'll import an example that currently exists. Actually, I can just import that tutorial.mpp, create a new workbook. There are, pardon me, some more advanced options here about importing particular tables and so on to make sure you've got the right information in your spreadsheet model. But I'll just run with the defaults. Let's say no. And this is what you will get. So that was based on a raw MPP file, this one. And now I've constructed what looks like the Gantt chart that we saw before in all of the tasks, but there is no at-risk functionality. This is now a raw workbook for me to build at-risk options into. Okay, and I can pick or identify specific pardon me, durations and start dates that I would like to make uncertain. So it's quite simple in that case, and in that manner, and quite straightforward to do that importing. There are a few extra features with importing, which I'll look at later, but for now it's enough to know that that's all you need to do. If I go ahead and look in the linking and syncing, you'll see that, as I said, the two files, the .mpp and the .xlsx file, are linked. They know about each other, and they know to be able to update each other as required. Now I'll put this one away quickly. Something that may occur to you when we open a small, pardon me, a small example like the one that we just saw, was that you may have a schedule that even after doing some reduction is still, say, 1,000 lines long, maybe even longer. You don't want to be going to each of those cells individually and putting probability distributions into durations or start dates. So we have a few tools to help you more rapidly build uncertainty into those models. So I've now opened an example file called Tutorial with Risk Categories. So it looks similar to before, but you can see with the color coding that I have here, multiple durations have been included. And you'll notice that they are, in this case, a triangular varying function, but there's an extra element here, a property function called risk category. So let's see what this risk category component is. In project model tools, I have risk categories. A risk category is a way of defining a group of tasks and varying them in an identical manner. So for example, up here in the training phase, we've got the planning. In the planning phase here, define training objectives, identify hardware, software, and so on. The duration is being varied as a triangular distribution, plus or minus 10% from the base value. In the equipment section, which is these risks here, it's plus or minus 20%. And the training section down the bottom, it's plus or minus 30%. Now, what are these groups and how do we construct them? Well, one simple way to construct a group is to start new. So this is going to be my resources phase. And I want to vary all of my distributions in one of the following ways. So for risk categories, there are these 5 possible options for you. I'm going to choose a PERT and say that it will be -5, and I want plus 40. So it's not one of my drop-down options, so I simply hard code 40. It will be the duration that I'm interested in, and I'm going to add these 4 tasks. Notice that I select the actual task name itself. Click OK. These tasks have now been identified here. -5 plus 40 from that base value as a PERT function. My resources group has now been identified. I click OK. Ask me if I'm sure. Yes, I'm sure. Now each of these cells has this risk vary function in it. Have a quick look at what that is. And here are the PERT distributions that I specified. -5 plus 40% from the base case. And cancel that. So I've now included these, all of these tasks in one click, essentially. So I could build large groups of durations, say durational uncertainty, which is the most common type, in terms of risk category. So you might have low risks, moderate risks, high risks, extreme risks. You might also have a column where you have actually a text field marked with a particular type of risk. This would be something that was set up in our project itself, generally, and you can include or utilize the add marked option where each of the risks has been allocated a particular, say, risk type, might be low, moderate, high, and by using the add marked option and checking the cell that has that word in it, low, mid, or high, I will quickly select all of those. So if you've put, for example, low, mid, and high risk as a descriptor, text descriptor in your project, when it gets imported, that will be here in the spreadsheet. And then perhaps you have, say, 5,000 line items. 3,000 or 3.5, maybe 4,000 of them are low risk. You can instantly select all of them using this, risk category option of picking all of the duration, sorry, all of the tasks that have been marked with that key phrase. Okay, just to let you know what that one is. For a smaller model, or one where you might have a dozen or more categories, it's probably not too slow for you to simply select those categories as we go. And obviously it doesn't have to just be the items in a particular phase. It's any task on the schedule can be put into a particular group. So now that I have my uncertainty in there, If I turn the dice on, and I'm pressing the F9 key, you might be able to see that some of these durations are changing, and that's being updated in the Gantt chart itself. Now, just to let you know, for a larger project, it might be quite unwieldy to have this Gantt chart there and updating live either during a simulation or while you're trying to build your distributions and so on. One of the options in application settings in the project section is to turn off the Gantt chart. This can make things run a lot quicker for you, and then later in charts and reports you can go and ask for the Gantt chart back if you want to include it. Okay, so the Gantt chart's useful for looking at in smaller models especially, and for instructional purposes about what's going on, but it might be too much for or unnecessary for a large-scale model, especially when you already have that in project itself. But we like to look at it while we're running a simulation so you can see the changes that are occurring in these modeling durations. Then I have my finish date, and so I'll run a quick simulation again. Now, some of you may remember that the old RPG, what we call that, was the at-risk that was an add-in to MS Project directly. Its simulations used to run quite slowly, simply because MS Project was a slow calculator. Then when we integrated MS Project into Excel with the at-risk interface, we faced the same problem of it running slowly. So now we have an option pardon me, for using an accelerated engine, okay, and that will be the default. So some projects, due to elements inside them, can only actually be correctly calculated using the standard or slower engine, but we can also run a check, and this allows you to tell, could I run, or could I use the accelerated simulation technique on my schedule? In this case, the answer is okay, so I know that I can use accelerated. Okay, so that's just an advantage that clients that have used our project integration before will notice, that the simulations now can run a lot quicker. Pardon me. Now, the categories had a limitation that there were only a handful, I believe 5 distributions that were available to you. I'll put that model away. So what I'll do pardon me, is show you an example where we can include a lot of information into the variables, sorry, into our uncertainties, including looking at the full gamut of our uncertainties. So for those of you who know that the world goes beyond triangles and PERT distributions, which is true, you might want to be able to include those, but still include them rapidly. So I'll point you toward the parameter entry table example. And in this case, we have an identified minimum, most likely, and maximum duration for particular tasks. In this case, triangles have been used, but the distributions have been created referring to cells in, or columns that are already in the schedule itself. So your estimators might put in 3-point estimates, and then you can utilize distributions to represent those. Now, the parameter entry tables themselves are identifiable here in our model tools. Pardon me. And in the parameter entry table distribution type, we have a big range of possibilities. Practically every distribution that we have. Okay. Common types, and then everything. An example is, say, a log normal, or even better, a log norm alt. So what I'll do is I will build a parameter entry table for you in a model that doesn't currently have one. So I'll go back to the tutorial with risk categories. And I've got these 4 tasks here, haven't yet been included pardon me, in the parameter entry table. So go to Project, Model Tools, Parameter Entry Table. I'll adjust the duration, and I want to use a log norm alt function to represent the variability. Use my selected tasks, add those. I'll grab these tasks, these 4, click OK. And now I can utilize these cells as the probability distributions, as the parameters, for these probability distributions, which are the quite sophisticated log norm alt functions. Same 3-point estimate. Those of you who have done training with me or have worked with me on, say, project cost estimation know that I heartily endorse the 3-point estimate idea, but also that doesn't restrict you to using triangle and PERT functions. Using the alt parameters, we can use log normals and so on, these more realistic distributions. In this case, you'll notice that they are the, by default, P5, P50, and P95 of each of these. So I might grab my base case as my P50, and I could do something simple like this equals, say, 80% of my base case, and this will equal 150% of my base case. And so now I have my low, mid, and high values for each of my variables. Let's have a look at what I've created. There is my log normal, built using 3-point estimates put on the spreadsheet, again, potentially by an estimator or someone who doesn't actually need to know exactly how to utilize that risk. But now we can. We've used these. We've quickly created log norm alt functions. There were only 4 here, but it could have been 40 or 400. We put in the parameters, our estimates for these, be they all selected individually or arbitrarily created using rules that make sense. And then, as always, run our simulation and get our results. So the risk categories and parameter entry tables are a way of allowing you to build your models a little bit quicker. Obviously, you can still go through cell by cell and pick distributions and parameters if you choose, but there are 2 ways of building things more rapidly. It's either my weekend gaps and so on. And here I've ranked all of my variables according to their effect on the output mean. These double-sided tornadoes are a new feature of version 6, so if you haven't played with those yet, I do encourage you to do so. We also have spider charts as well. So I'll close that down. Pardon me. Now, I mentioned earlier that when importing a .mpp file, there are a few more sophisticated things that we can do with that. And I'll utilize the schedule audit example model to show you this. So that is quite literally an option called schedule audit, where it looks at your schedule and finds things that are potentially errors or that you should maybe look at. So for example, in this model, if I go to project schedule audit, check the audit, and I see that I have some pardon me, tasks here that have a finish no earlier than constraint. Now that may have simply been a legacy of previous modeling that was just done in project, but it's potentially not realistic. So this audit allows you to identify these things and potentially make changes if you need to. In this case, we've got to start no earlier than constraint, and that itself might also be unrealistic, just a mistake that was made. We can start this as soon as the previous task has been completed, rather than having a delay. Likewise, we have, in this case, a task, it's this one down here, identify location for training, that has no predecessor. So it's variation in that will have little to no impact on the model. Perhaps it should have had a predecessor. So these are the sorts of errors or potential issues that the schedule audit option allows you to have, because obviously what we don't want is to run a simulation on a schedule that doesn't make any sense. As soon as we have any sort of illogic in our schedule, then we no longer have meaningful simulation results. So the schedule audit tool allows us, or gives us an extra weapon in the fight against illogical modeling. We can make those changes, it identifies them for us, we make the changes, and then we know that our model is legit, then we run our simulation and we can trust the results that come out of it. Now, there are certain things that occur in scheduling that visually don't really appear in regular Excel spreadsheet modeling. Or if they do, we deal with them in a different way. The notion of mutually exclusive and exhaustive states. In other words, you might refer to this as probabilistic branching. This is a structural issue quite specific to a schedule model, where after a particular task has been completed, the next task is uncertain. I have an example here, pardon me, which is probabilistic branching. And in this particular model, after we've done our market research or product testing, we may not do further testing. We might go straight to a local rollout. After locally rolling out a new product, we may in fact go straight to full national rollout, or go through to region 1, then 2, then 3, and so on. There are different possibilities. So if I run a quick simulation for you, we see what looks like a potentially unusual situation, and that is a multimodal finish date. Lots of finishes here, lots of finishes here, some more down here. Is that legitimate? Well, I'll run a longer simulation. It's 500 iterations now. Don't need to watch it updating. Let's just get the simulation to finish. And you can see there are distinctly different modes. Now, these have been created by the probabilistic branching which is built into this model. And I'll show you that branching now. So clearly, 3 separate areas in which you might finish. You might finish very early, or a couple of weeks after that, or a couple of weeks after that. These are these 3 different centers of likelihood that we're looking at. So what's been built into this project is a probabilistic schedule. In model 2, is a probabilistic branching. The probabilistic branching option inside model tools shows that after startup, we think there's a 70% chance we'll do some more market research, a 20% chance we'll go straight down to the region 1 rollout, or a 10% chance we'll go to some limited product testing. Likewise, after the region 1 rollout, pardon me, we might go and do a region 2 rollout, or go straight to the full national rollout. The effect this has visually, if you like, is the following. I'm doing some random sampling. There we go. I finally got an option that changed. So here, after startup, instead of doing more market research, we went straight to product testing. So you see this task itself has been left out. In this case, after the region 1 rollout, we've gone straight to region 3. So to the full national rollout. So the idea of probabilistic branching is to allow you to include these logical changes that might be made to the structure of your schedule based on mere chance. If it is indeed a legitimate possibility that after the startup, things will go so well that we will go straight to rolling out the product launch in region 1, then that needs to be acknowledged by the schedule. So each of the branches that we have indicates a range of mutually exclusive and exhaustive possibilities. So after startup, it either goes to market research or product testing limited or region 1 rollout. It can do all of them in order, but it doesn't have to do these steps pardon me, along the way, because we may make a decision to go straight to the region 1 rollout, but then slowly roll out across the regions, for example. Okay. So for those who are adept at their at-risk in Excel modeling, this is essentially the equivalent of a risk discrete function. It's similar to the notion of a decision tree model as well, where we get to a certain point and we have different choices. We don't simply go from one task to the other. Okay, and that branching could potentially also be used to indicate an event that occurs. So after a task is finished, we may then need to perform some other additional task, restructuring, reinforcement, whatever it might be. So there's some chance of that task occurring, but it might not occur. So we could have a probability that after we finish a particular piece of work, we may then need to do some additional restructuring or wait for approval for the next phase, something like that, or we might just go straight and do the next thing. So that type of alternate options or different realities, different possibilities, can be modeled using probabilistic branching. But once you've got those branches in there, the simulation itself runs with all the rules you would expect, and we can run a simulation as you saw me do to begin with. I'll show you a quick example of including probabilistic branching. And let's say we will add, if it gets to region 2, it'll either go to region 3 or straight to a full national rollout. And let's just say it's 50-50 for simplicity. So if we get to a region 2 rollout, it might then go to a region 3, or we might go to the full rollout and ignore just an individual region 3 rollout. So now, scroll out, have a little look. Turn the dice on. Here's an example straight away, where after region 2 rollout occurred, it went straight to the full national and skipped the region 3 task. Here's an example where it went straight from region 1 to the full national, so there were no intermediate steps. Okay, going through the various possibilities here. And here's one where it goes from region 1 to region 2 to region 3, and then to full national rollout. So all of the possibilities with the probabilities that I marked. Okay, and I'll put probabilistic branching away. Pardon me. I'll mention that it exists, but I won't show you an example today. We can also include a probabilistic calendar. So I'll just explain the significance of that. We know that we can allocate calendars to resources in project. What we can do is include probabilistic non-working days or non-working periods. So for example, you might have data from the BOM that says during December, on every single day there is a, say, 20% chance of enough rain that we have to stop work. So we can include that in the calendar itself for a particular resource, say, such that in every day in December, there is a 20% chance that resource essentially will be unavailable. Likewise for sickness and so on. So there will be a range of possibilities there from getting no rain to getting lots of rain, and therefore the final finish date includes accurate information about what the rain delay is. This is far more accurate and sophisticated than simply saying, well, let's add 7 days for rain delay to the schedule. Now we can look at the probability of needing to add 7 days, 10 days, 3 days, and so on. That's the probabilistic calendar option. The next example I'll look at is something that's quite important and, dare I say, critical to schedule modeling, and this is the probabilistic or stochastic understanding of your Gantt chart. So if I get a model and I look at my Gantt chart, something that we are used to from the deterministic world is the Gantt is the Gantt. This is what my project looks like. Therefore, I can see precisely which tasks lie on the critical path, and therefore I only have that one critical path. This task is critical, this task is not critical, and so on. This is, however, unrealistic. If I were to zoom in on this little section or selection of tasks here, currently these three are all critical and these two are not. They don't lie on the critical path because if I just look at a small change in one of these, it is not changing the overall duration of this phase, say. However, if I look at this task here, identify location for training, if this task were to take longer than this task, now it is actually impacting the overall duration of the project. Likewise, this little task here, it might go long enough to influence future tasks, and this becomes non-critical. What this very simply shows you is that there is no such thing as the critical path. For each iteration in your simulation, there is a new potential critical path. So if things turn out a little bit differently, some tasks may or may not lie on the critical path. So we go from a fixed Gantt chart and fixed critical path to the idea of the critical index. Now, the critical index gives us, very specifically, the probability that a given task lies on the critical path. Now, by calculating that, we get to establish just how critical a particular task is. If something, even with variation in start dates and durations, always lies on the critical path, it will be given a critical index of 100%. However, something might lie on the critical path sometimes and not, and maybe it's only been critical in 40% of the iterations. Therefore, it receives a critical index of 40%. So this can be a very big change to the way we think about our scheduling, but it is absolutely realistic. In the simplest of schedules, where every task is finish to start, obviously they all lie on the critical path. Another simple structure might be a collection of big tasks and a few little ones that never have the ability to push back the finish date at all. However, that's not the case in general for most projects. There will be a chance that various tasks will or won't be on the critical path, and we'd like to know what that chance is. So instead of saying something is critical or not, we might now draw a new line in the sand at maybe 70%. If a task has a critical index of at least 70%, then we will deem it to be important, or maybe 50%. But something around 70 might be a good start. That's certainly the default value in the software for indicating importance, but you can change that. So it's a brand new step, and it's one of the new pieces of communication you may need to give to your project managers or to your board of directors, management, your clients, that we just don't have a critical path anymore. Now, if I turn the dice on here, scroll back, if I look at different options, you can see that some of these tasks do or don't happen. Sometimes they get branched away, sometimes they're very small, sometimes they're much longer. And you can see that the same relationship isn't always being maintained across all of the tasks. Some things pop out ahead, some things sometimes stay behind and aren't important. So we'd like to measure that. We will do so by running a simulation, of course, and checking our results. And then we're going to generate ourselves a probabilistic Gantt, as well as getting our critical indices. Now, just to show you what I clicked then, in project settings, before I run a simulation, I will ask to calculate the critical indices for all of my tasks, as well as get the statistics for a probabilistic Gantt chart, should I want one. And in this example, I do want one. So I'm going to run a simulation now. Run it with, say, 500 iterations. Of course, we'd run a longer simulation to get real results. This is just for the purpose of the exercise. So it took about 6 seconds for that, so I could have, in a minute or so, easily run a few thousand iterations. Now I'm going to go to my charts and reports section and ask for a probabilistic Gantt chart. Now notice the options here. We could track different outputs. But what I will also note is that on the chart itself, I want to include the average start and finish date for all of those tasks, as well as the P10 start date and the P90 finish date. So I'm going to get a range of possibilities. I could go further into the tail if I was interested by putting in, say, P5 and P95. I will also display the critical index on my report and also colour highlight everything over, say, 70%. I'll click OK, and I get my report. Now what this shows, pardon me, is the different probabilities that any of these items were critical. Initially we see 98.8 and 1%, 0%, 99% and so on. So they're essentially either always critical or always not in practical terms. But here I have some examples where it's 40% or 30%, 60%. It would be up to me, my organisation, to determine whether or not these are worth looking at. But now I know that just because perhaps they were on the critical path in the base case doesn't mean they'll be there a lot. This allows me to really narrow down and focus my energies on the key risks themselves. So 59, there's a 90 there, and you'll see that everything over 70% in terms of critical index has been coloured. If I dropped that down to, say, 55%, these would also be coloured. Now the next thing that's very interesting to look at here on my report is the probabilistic Gantt. Now, quite a long model here, but in blue and black horizontal bars, at risk is showing you the base case. So that is the original Gantt chart that sits here. That's what it looks like. The pink and red sections show you what happens when we actually run a simulation. So for example, this training plan phase is represented by this black bar here, actually has an average start there, which isn't too different, but an average finish date, on average that is, well after the deterministic finish date. It has a P95 finish date way out here, and a maximum finish date in our 500 iterations way out here. So this bar from end to end represents the full range of values we saw in our simulation. The inner pink thick bar here represents, in my case, from P5 to P95, so a 90% confidence interval. And then these diamond markers here and here indicate the average start and finish dates. So we can see how our original schedule doesn't provide us with a lot of useful information about how early we might need resources to start a particular phase, or how late in the piece we might still be actually doing some of these tasks. But my probabilistic Gantt gives me that information. Okay, and this is just an Excel report. There's no at-risk functionality in this. This can be emailed around to anyone who can view an Excel spreadsheet, and they'll be able to see these results and also see the critical index. An extension to the idea of criticality is that of cruciality. Now, cruciality takes criticality one step further and says that something might lie on the critical path, but maybe it only adds a total variation of 1 day, total, maximum impact, to, say, a 5-year project. So even though it's on the critical path, it's not actually that important. So one way of measuring that, pardon me, is with cruciality. Now, cruciality multiplies the critical index by, pardon me, usually the correlation, so a sensitivity coefficient. Therefore, an item that lies on the critical path, but if it's big or small, it's not really showing up as a big increase or decrease in the duration of the overall model, then it won't be deemed crucial. So it still might be critical, technically, but not actually important. So cruciality, I won't run the model, but cruciality is another key result that again allows you to drill down to just those tasks that are actually key, that are actually important to you. Okay, so there's a few examples looking at the structure of your schedule and how at-risk and will interface with that in the Excel environment to allow you to do some advanced analytics. I'm going to take that a step further. Let's look at something that is in at-risk but is also in the project interface, and that is correlation. It will be very, very common for a lot of your tasks, be they as measured by start date or duration, to be correlated. The same sorts of things that will make a particular task take longer, such as environmental conditions, workforce skill level, and so on, just simply the ability of your project manager to keep things going. This will mean that multiple tasks will either all take longer or all be finished earlier. What I've just said in that wordy description is essentially they need to have a correlation structure. Okay, correlations like this. So in my pardon me, in my model itself, I have various tasks, some of whom are correlated. I can tell that by the risk format function. So I have a training setup matrix and then a training time matrix. So if say my trainer is of good quality, or the training materials are set up well and so on, maybe all 4 of my training sessions are likely to be quite quick. If the opposite's true, however, and it's a bit of a shambles, maybe all of those tasks will be longer. What's unlikely is that Group 1 training takes 25 days, Group 2 takes 15 days, and Group 3 takes 25 days again, and so on. I'm suggesting here there's a good chance that these will all be related. And so they've been correlated with 0.6. Likewise, the pardon me, development of the training program, these 2 variables have been correlated as well. So if I run a quick simulation, we'll see that whilst installing the software and installing some test drives, there's no relationship between how long it takes those things to do. Pardon me, the training setup is related to the developing the class program duration. So this means that my model, with the correlation, both has the capacity for being a lot shorter than I would expect, or a lot longer than I would have hoped for. This has the effect of increasing the overall level of uncertainty. However, it has made it more realistic, because these pairwise relationships are far more likely than if I didn't have them correlated at all. I now know my results are going to be more realistic. Likewise, there is correlation between these variables. And then the results that I see here wouldn't have as many results in the very high and very low section without that correlation matrix, but then I'm not understanding how long pardon me, how long it might actually take if all of these things do start to get delayed. I could test that as the same way I would test an Excel model by using sim table functions to compare the correlated model to the non-correlated model. If any of you aren't familiar with sim table, I do suggest you look it up. It'll probably become part of a future hints and tips at-risk webinar that we might hold. It's certainly part of our training sessions, but it's a very, very useful feature for comparing modeling assumptions. In this case, the assumption of correlation is something that I could compare or test. But otherwise, the rules about including correlation matrices are identical whether we have a schedule model or whether we have a regular spreadsheet model, if I could name it that. Now let's look at an example where we start to include not just the schedule itself, but a risk register that could impact or influence our schedule. So this is the risk register or simple risk register example. In this case, I have a couple of tasks. Some or all of these are influenced by elements that I've got in my risk register. Now this risk register worksheet is one that is built by the user in Excel. It doesn't have anything to do with MS Project. So where resources and tasks are imported from Project, the register is something you can build yourself. So in this case, I have a simple risk register where I have 3 risks, and each of these can influence my tasks here. Now they can influence them in a couple of different ways. One is to influence the schedule by adding a certain number of days to the model. The other is by influencing cost, or of course both. Okay. Let's look at a simple way of including a risk register like this, or information like this, into your model. The cleanup task is a risk PERT function with these parameters for the total number of days, but also has this plus risk register L6 component to it. Remember, it's just a spreadsheet, so you can write anything you want in a cell. What's risk register L6? L6 is here, which is the impact in days of this risk. Now, if I turn the dice on, you see this risk only happens 20% of the time. So it's still not happening, still not happening. In this particular iteration, it has happened, and it's added 32 days to the plan. So it didn't occur, didn't occur, didn't occur, and then in one iteration it finally did, this environmental risk. And we can see that the cleanup now takes 60 days. Even though that particular task is defined with a maximum of 35, but I have the potential for the duration to be much longer. Okay, so there's a very simple, logical way of combining your risks to your tasks. Another example will be in costs, where, by the way, of course, any of these things can be, any cell can become a probability distribution, but I might want to include a cost impact. And that could be a little bit trickier to do. However, we have a new set of functions, one of which is the risk project add cost function. What risk project add cost allows you to do is to select the amount of the additional cost. In this case, it's S7, which is here the cost impact. The date on which it occurs, because obviously in a schedule model, it's important to know when the costs are being incurred, not just the total cost at the end. And so this function, risk project add cost, will be read by at risk, and randomly, if I keep the dice on, add, in this case, 104,000 to the model on the 13th of February. It added nothing because the event didn't occur. Anytime it does occur, a cost will be added on a particular date. So that's a standalone risk project add cost function. One thing to note for those who may have picked up on this idea before, if you've got resources being charged based on the duration, if I include a risk here, this additional duration will become part of the cost. Whereas I can use my add delay and add cost functions, in particular the add delay function, to add delay to a task without incurring an additional cost. Perhaps you've paid for it. It doesn't matter if it takes longer. You don't pay extra. It's only a time penalty, in which case the risk project add delay function will be the one to use. I'll show you that risk project add delay function. It says, what do I need to add the delay to? In this case, design. The delay length will be the schedule impact here, L5. And any cost, well, that's going to be the cost here in S5. There's some brand new functions in version 6 that we can use to apply a risk register to our model. Okay. So one has been included using, if you like, brute force, and there are particular implications of that. The other is utilizing these new functions, add delay and add cost. I'll put that one away. Now the last example I'll show you is the risk register and advanced modeling example. But before I get into that, just a few other things that we haven't looked at, but you can look at in your own time. The pardon me, add resource use functionality is another piece of sophisticated modeling. I won't cover that today, but that's something for you to look up. Once you've got the basics of how the interface works, there will be things for you to go and include in the model to do things that you otherwise can't do. Without those functions, it's very difficult to do these things. Likewise, there's some information on using dates with at-risk. And there is also integrating VBA for Excel code with your projects. Okay, so that's obviously well beyond the scope of a brief talk, but just as we can use macros to help make our normal at-risk spreadsheet modeling a little bit easier, we can also do the same with our project modeling. So I'm going to finish by looking at the risk register and advanced modeling example, which has several of the techniques that we've already discussed built into this model. So as you might note in the explanation, there are some correlations there. There's the use of hammock tasks and how they can be built into your modeling. Also the use of pardon me, add delay and add cost in the risk register. But we've seen a lot of these things already. So I instead want to show you timescale data. Now, this is where we can really add a lot of value in terms of our planning and so on by looking stochastically at either cumulative or actual costs over time. So we can see not just how much the final cost might be, because I can have total cost as a variable. I'll run a quick simulation. But what I also want to be able to do is understand how that cost will be spread over the duration of my project. How long into the future might I still be asking for certain amounts of money and how much money? What is my average cumulative cost? How does that compare to my deterministic model? And so on. So I have here my model for the total cost. But was this cheap and quick and long and expensive, or some combination in between? How did I arrive at this total cost value over time? And it's timescale data that builds that information for you. So if I go to Project, Charts and Reports, Timescale Data, it allows me to create a chart for that cumulative accumulation, pardon me, repeating myself, of cost. Let's have a look at the settings. If I want to collect timescale data, I need to select it, and then I select what it is that I'm going to look at. So here I've got the entire project is what I want to look at, but obviously I could look at timescale data for particular components, which might also be useful, or indeed resources, or every summary task. I'll just pick the cumulative cost, but you can see you can choose actual cost over time, so we'll see that go up and down, not just continue to accumulate. All these other elements that we could be tracking. Okay, so I've run my simulation. That was already turned on, so I should be able to create a report for timescale data. I'm going to track the minimum, maximum, P20, P80, and mean cost, and also compare it to my deterministic model. And so if I look at the chart here, I see my deterministic model had me finishing on this date and therefore incurring no extra costs. However, once I include my understanding of the uncertainty and the correlations here, I also see that there is pardon me, only a very small probability that I will actually be finished by that point in time. You see, it basically matches the P20. So there's an 80% chance that I will actually require more than what my deterministic model showed. The yellow line shows the average cumulative cost, the blue line the P80, and the max is this green line up the top here, likewise the minimum down here. So now I can see not just the costs that might be incurred, but how late into the project I still might be incurring those additional monies. Okay. So that's also available in box plot form, but I think that this chart looks prettier, just to be honest with you. The data itself is generated so you can see what the actual values are for each, in this case, month. Pardon me. So we could track or do additional analysis on specific statistics. We aren't stuck just looking at the graph and pretending to be able to read off certain results. Okay, so that's timescale data. It's again another report that is specifically useful to schedule modeling. But just as a little tip, make sure you, pardon me, in the settings, ask to include it before running the simulation. Otherwise, the data won't be stored, and when you've run a simulation and you go to ask for the report, it says there's no data. Just the same with the critical indices or the information for a probabilistic Gantt. Make sure you have these selected prior to running a simulation to ensure that you can actually get those results afterward. Okay, so I'm going to wrap up the discussion there. Just the key elements for you to take away. One, by doing schedule modeling inside Excel, we basically have no logical restrictions now on what we want to do with risk register or combining it with another cost model or a cash flow model or whatever we need to do. Because it's all in Excel, we can do it. It's not just taking a photo of the schedule and then making some unrealistic assumptions. It actually uses the rules of your schedule in terms of precedence and succession and so on in your simulation, so it keeps things realistic. All of the things that we talk about for regular spreadsheet modeling hold true. The need to pick an appropriate distribution, the ability to do distribution fitting to data, picking the curve, simulation settings, all of the graphs you're familiar with, these all still hold true, but there are a few extra little bits and pieces that make projects a little bit special. One is the ability to rapidly include uncertainty to large bulks or large chunks of your schedule. The other is some particular reporting, specifically the probabilistic Gantt chart, the critical index, and cruciality, as well as timescale data reports that will be specific to projects, but as you saw, very, very useful information. Okay, one other thing, of course, is just another reminder. This is being recorded, so you'll be able to watch it again if you'd like in a couple of days' time. And if you'd like to actually do or go through the examples that I have done in your own time, I've limited myself to utilizing only the example spreadsheets. So you could watch this presentation again and then go through the examples along with those in your own time so you can actually see how I'm doing the things that I'm discussing with you. So if you do have any further questions, please feel free to contact our office. As I mentioned, if you are in Australia or New Zealand, you'll speak to Duncan Hickman. If you're from the rest of the Asian region, please ask for Freeman Liu. Otherwise, I hope to see some or all of you at the decision tree analysis seminar tomorrow, same time tomorrow, using Precision Tree, or at one of our future webinars or training sessions pardon me, in our region. Please check the website. We have lots of things going on, so hopefully we can get you along to one of those, and I'll be able to speak to you in real life soon. Okay, so thank you very much. and we'll finish our session now. Hope to see you tomorrow.